Okay, so my critical numbers from my second derivative would be x is equal to 0, or 1 over 2 plus or minus the square root of a half. Okay, so let's set up a number line here and check our intervals. Here's 0, here is negative root of a half, here's the positive square root of a half. And let's choose a number. Oh, let's go over on this side. Bigger, like let's say 10. If I put 10 into here, that's positive. 10 squared times 2, 200 minus, that's positive. So concave up. Between 0 and a half, what's the number between 0 and the square root of a half? Anybody know what the square root of a half is approximately? About 0.7. So let's choose something like in between, like 0.5. 0.5 would be smaller than the square root of a half. Okay, so if I put a 0.5 in here, that's positive. 0.5 squared is 0.25 times 2 is 0.5 minus 1, this is going to be negative. And can you see that if I put in a negative 0.5, I'm going to also I will also get, I'll get a positive, won't I? Because if I put a negative in here, that's negative. I put the negative 0.5 in here, that's negative. I got a negative times a negative is a positive. Okay, and if I put in a number less than negative a half, like negative 10, that's negative, and this would be positive, so negative. Okay, so I need to talk about where's this concave up? 2 intervals, from negative root 1/2 to 0, and from the positive square root of a half to infinity. Where's this concave down? It's concave down from negative infinity to negative root of 1/2, and from 0 to the positive root of a half. Okay, and because the concavity changed, we have inflection points at x is equal to negative root 1/2, at 0, and the positive root of a half. Okay, and the only thing left to do here is to set up a t-chart with all of those critical numbers. So here's x, here's y, and in order, including these x-intercepts. So negative root of 5/3 comes next. Negative 1, negative root of a half, 0, the positive root of a half, positive 1, and positive root 5/3. Okay, so the zeros of the function, where did I have those? Right here, the x-intercept, 0, 0, 0. When x is negative 1, so let's look at our original function. If x is negative 1, this is going to be a negative. This is going to be a negative 3. No, it's not. It's going to be a 3 minus 5, which is going to be 2. This is going to be a negative 2. No, sorry. I'm going to get a negative times a negative would give me a positive 2. If I put in a positive 1, then I should be getting a negative 2 because it's an odd function. If I put in a positive 1, I get 3 minus 5, negative 2. Nobody wants to do the square root of a half, do they? So let me just tell you, I put it in there and I got 1.23. and negative 1.23 because it's odd symmetry. Okay, so let's mark that this here is an inflection point. This was an inflection point, and this was an inflection point. Okay, we got 0, 0, zeros. We're not going to say that. And we did get a max. Where was our max at? We had a max right here, and we had a min right here. Okay, so let's get all these points graphed, and then using this information, we're going to get a really nice, accurate sketch. I know that that graph isn't quite big enough. Here. So I'm going to put this on here. And I'll just pass this around. You guys can graph it to the best of your ability in that tiny little space. But I'll pass these around, and you can just take one of these graphs and put it on your page. They're hard to peel off. Just take one and pass it on. Okay, so we've got all these decimals. Let's see, this is about 1.3. This is about negative 0.7, positive 0.7, and this one is about positive 1.3. Okay, so let's do 2, 4, 6, 8. This point is 1, and here's negative 1, here's 1, here's negative 1. Okay, so we'll use that for our scale. And I'm just going to overlay the axes. Okay, so the important points to show here are when x is negative 1.3, so negative 1, 1.2, negative 1.3, so right about there, y is 0. When x is negative 1, y reaches a max of 2. When x is negative 0.7, 2, 4, 6, right in here, y is 1.23, so right about here. X is 0, y is 0. X is about 0.7, 2, 4, 6. Right here, negative 1.23. And when x is negative 1 point, or when x is positive 1.3, y is 0. So 1, 2, 3, 4, 5, 6, 7 key points that we've graphed. So it's a quintic function with a positive leading coefficient. It's starting down here in this quadrant and moving up to its max, coming down through the 0 to the min and back up, like that. Let's remember that we've got this point of inflection right here, right here. So this function is concave down from negative infinity to this negative square root 2. Let's just negative root, and I said 2 and I meant to say a half. So concave down. So your function is going to look something like this. And then from this to 0, it's concave up. So you've got the curve coming like that. And now from 0 to this positive root of a half, the function is concave down. So it squiggled through the axis there. So it's concave down ooh, to this inflection point. I know what I missed. I missed this point here. X is 1 and Y is -2, my min. So this was concave down, and then from this point on, it's going to be concave up, and just keeps on going. So there's our graph of that function, and our key points here. We've got a local max, we've got a local min, we've got an inflection point, and another inflection point where the concavity changed. So when you graph that on your graphing calculator, it's easy to see the 1, 2, 3 zeros, but not always easy to know where the max and min occurred unless you use your feature. But what's hard to see are these three things, those inflection points. Okay?